Assalamu alaikum wa rahmatullah, and thank you for letting me present my work on the title U-band multi-wavelength Brillouin-Raman fiber laser. First, I'm going to start with the outline to the presentation, which include introduction and motivation, research gap, research objectives, research scope, literature review, proposed design, proposed methodology, research outcomes and deliverables, result and discussion, and references. Introduction and motivation. Multi-wavelength fiber laser has become a research hotspot and caused enormous interest and attention in the world, as it has many different applications, including the DWDM as shown in figure here. The DWDM use multi-wavelength as the implementation of such a multi-wavelength fiber laser in the DWDM will save the cost to some extent. Also, the multi-wavelength fiber laser can be used for long distance measurement of strain and temperature. The multi-wavelength fiber laser can also be used for phase antenna array because the phase antenna array use laser source with multiple wavelength for its operation. Moreover, the multi-wavelength fiber laser can be used for the generation of microwave photonic, and the most important application can be a promising solution for the next generation optical passive network. When we come to the feature of such a multi-wavelength fiber laser, it has high bandwidth, low cost, good compatibility to fibers, tunable, and compact size. The research gap. Multi-wavelength fiber laser sources are currently in huge demand as they are employed in the DWDM and the next generation optical passive networks, which shows a promising outlook in meeting the ever-growing demand for telecommunication capacities and internet traffic. Therefore, there is a dire need to work not only in the current optical window, including C and L bands, but also work on the untapped bands, such as long distance, such as ultra-long U-band operating from 1625 nanometer to 1675 nanometer. There is an existing work in the U-band, but have limitation for the one that use semiconductor optical amplifier and booster optical amplifier, which has limited number of channels that has been generated. For the one that use Brillouin-Raman fiber laser in the U-band region, it has limited number of channels that is generated using a single Raman bump. This is the limitation of this work. And also it has a narrow bandwidth of up to 23 nanometer. What are the requirements of the WDM application? It needs laser source with high number of channel, laser source with a high spectral flatness and good optical signal to noise ratio, laser source with wide tunability. When we come to the research objective, this research is conducted with the following objectives: to design, characterize a new U-band multi-wavelength fiber laser with double wavelength spacing of 0.16 nanometer or 20 gigahertz spacing with high number of channels using a single Raman pump source. Second objective, to optimize a simple multi-wavelength Brillouin-Raman fiber laser with enhancing its spectral comb in terms of channel number and tunability. The research scope: the multi-wavelength fiber laser is generated with using different gain medium, including Brillouin thallium fiber laser, Brillouin erbium fiber laser, Brillouin fiber laser, and Brillouin-Raman fiber laser. In our work, we try to focus on these two in a blue color to integrate them together to form what we call the hybrid Brillouin-Raman fiber laser, which is currently generated in different bands. In our work, we focus in the U band, which generate either single spacing and the double spacing, and we focus on double spacing, which can be generated by using the single ring cavity or linear cavity. In our focus, we focus in the linear cavity, which can be generated by two virtual mirror at the end of the cavity, or physical mirror, or can be used by virtual mirror by taking advantage of the relay scattering induced by dispersion compensation fiber. The literature review here is the recent work on the U-band multi-wavelength laser, but have used different gain medium for the operation. And the reference number 6 here, use the semiconductor optical amplifier for its as a gain medium and generate around 20 channels. And in this operation, it cover around from far L 1613.7 to 1625.9 nanometer. And in the U-band, it covered from 1626.5 to 1643.6 nanometer. And it has limited number of channels that is generated. This is the limitation of this work. And for the reference number 4, it used a booster optical amplifier as a gain medium and generated around 13 channel and cover from far L from 1623 to 1626 nanometer, and in the U-band cover from 1626.7 to 1639 nanometer. For its limitation, it has generated only limited number of channels. for the critical review on the multi-wavelength Brillouin-Raman fiber laser in the U-band. Here is the benchmark paper which is published before 2 months, and it is the same as our work in the U-band, but have some limitation. We try to address them in our work. Here is in reference number 5 at the end of the presentation. It used Brillouin-Raman technique and generated around 136 flat channel with 18.4 gigahertz channel spacing with 26 dB as average optical signal to noise ratio over 23 nanometer bandwidth, and its operation cover part of the U-band in the region 1654 to 1675 nanometer, but have some limitation. We will address them in our work. The first one is the setup need high Raman pump power of about 2.276 watt, and also the second one is limited number of channels that is being generated from a single Raman pump. The proposed design for the U-band multi-wavelength Brillouin-Raman fiber laser is based on 4 open cavity because it has some feature which include high number of channels, wide bandwidth, good optical signal to noise ratio. Here is the proposed design, which consists of the TLS or the Brillouin pump and the circulator 1, which provide a venue for the Brillouin signal to enter to the cavity and provide an avenue for the also for measurement, and the dispersion compensation fiber work as a virtual random mirror inducing the relay scattering, which to generate the multi-wavelength, the WDM here provide an avenue for the Raman signal to enter to the cavity, and the circulator 2, which was used to monitor the laser because sometimes the Raman pump is not stable, and we try to monitor it using the optical power meter, the output of the circulator. The research methodology start by designing the U-band multi-wavelength Brillouin-Raman fiber laser with full open cavity. Then we run the experiment. After that, we determine the design parameter, which is the Raman pump power, Brillouin pump wavelength, Brillouin pump power, and the CF length. Then we determine the performance parameter, which is a threshold power, number of channel, signal to noise ratio, signal flatness, tuning ring, and the stability. Then we test the amplified spontaneous emission as the Brillouin power is switched off, and the Raman pump wavelength is set at 1650 nanometer, and the Raman pump power is varied from 500 to 1.5 milliwatt. Then we measure the threshold power. We measure the effect of the Raman power on the number of channel, signal to noise ratio, signal flatness. Number 3, we measure the effect of the Brillouin wavelength on the number of channel, signal to noise ratio, signal flatness, and tuning ring. And number 4, we study the effect of the Brillouin power on the number of channel, signal to noise ratio. Number 5, we test the stability of the optimum Raman pump power, Brillouin wavelength, and Brillouin power. Finally, we measure the laser efficiency. If we have an optimization, we vary design parameter and go back to run the experiment again. If not, we get the already optimized multi-wavelength Brillouin-Raman fiber laser, analyze the result, and end the process. When we come to the research outcome and deliverable, the output of this research would be the development of the U-band multi-wavelength Brillouin-Raman fiber laser with high number of channels with double frequency spacing or 20 gigahertz using a single Raman pump that was achieved. The result from this study was published on conference proceeding 2 months ago. Results and discussion. Here is we follow the methodology step by step to measure the results. We first start by measuring the amplified spontaneous emission and the power threshold. The amplified spontaneous emission is measured here in order to know at which wavelength the Raman achieves the highest peak gain. This is important to put the wavelength of Brillouin next to the Raman peak gain. This is achieved when the Brillouin signal is switched off and the Raman power is taken at different power, which is including the 960 milliwatt, 1100 milliwatt, and 1180 milliwatt. At this, and we can see here from this figure, the Raman achieved the highest peak gain at 1660 nanometer wavelength. This is which is far from the original Raman signal by 110, which is equivalent to 13 terahertz. As we can see here, as the the power increase, the Raman begin increase to reach the highest gain at 1180 milliwatt, which is the highest power in the blue color. Then the power threshold is investigated when the Brillouin power is set 11.8 dBm, and the Brillouin wavelength is set at 1640 nanometer, and the Raman power is varied from 500 to 700 milliwatt. At this power is called the threshold power, because at this power, the first stock line is generated, which represents the odd signal, and it is separated by 0.167 nanometer from the original Brillouin signal, which is equivalent. This separation is equivalent to 20 gigahertz or double spacing. Then the evaluation of spectral comb with the increment of the Raman power is investigated. When we increase the Raman power from 700 to 740, a spectral comb with only 3 channels is generated. This is because, and as shown in this magnified view, this is because at low power, the relay scattering is insignificant at the low power, resulting on only 3 channels with only 3 stable channel. Then when we increase the Raman power to 780 milliwatt, spectral comb with chaotic glazing is generated with only 4 channel that is stable, as shown in this magnified view, because at this power, the Brillouin stock line cannot overcome the self-glazing mode, resulting in more chaotic glazing. Then the evaluation of spectral comb with increment of the Raman power is investigated. Once we increase the Raman power to reach 860 milliwatt, a spectral comb with stable channel is generated. This as shown in this gray color, because self-glazing mode is suppressed and resulting in high number of channel. Also, continuing to increase the Raman power to reach 1260 milliwatt, a spectral comb with high number of channel is generated. This is because the self-glazing mode is totally suppressed, resulting in high number of channel with stable spectral comb. Then the evaluation, the effect of the Raman power on the Stokes line count and optical signal to noise ratio is investigated when the Brillouin wavelength is set at 1640 nanometer and the Brillouin power is set 11.8 dBm, and the Raman power is varied from 860 milliwatt to 1300 milliwatt. As shown in this figure, the total Stokes line, which is in the black color, increased gradually with the increase of power from 860 to 1300 milliwatt because of the more transfer of energy from the Raman signal to the Brillouin Stokes. And you can see here at 860 milliwatt, about 220 channels generated and increased gradually to reach 255 channel at 1300 milliwatt. Also which is the highest number of channels. Also, the average optical signal to noise ratio is investigated to increase the Raman power, as shown here. As we increase the Raman power, the average optical signal to noise ratio decrease gradually, because when we increase the power, the total number of channels is generated. The highest the number of channels is increased, so the energy is not become enough to be distributed over the number of channels, resulting on decreasing on the average optical signal to noise ratio. As we see here, the average optical signal to noise ratio at 860 milliwatt is 23.7 dB and decrease gradually to reach 20.96 dB at 1300 milliwatt, which is the least average optical signal to noise ratio. After that, the 3 dB flat channel is investigated with the increased Raman power from 860 milliwatt until it reached 1100 milliwatt. The flat channel achieved the highest flat channel with 240 flat channel, which is the optimum, because at this power, at 1100 milliwatt, the Brillouin signal has the optimum value. After that, any increase of the Raman power will result in a decrease of the flat number of channels because the Brillouin signal becomes saturated. More analysis on the effect of the Raman power on the average optical signal to noise ratio is investigated, as we with the same parameter Brillouin wavelength, and the Brillouin power is taken at the same parameter, but the Raman power is set at 860 milliwatt to 1260 milliwatt. As shown here, as we increase the power from 860 milliwatt to 1260 milliwatt, the average optical signal to noise ratio decreases gradually. As we see here at 860 milliwatt, which is in the black color, has the average optical signal to noise ratio of about 23.79 dB and decrease gradually to reach 21.2 dB at 1260 milliwatt, which is in the blue color. As we increase the power, the average optical signal to noise ratio decrease gradually. Also, the separation between each channel is about 0.167 nanometer, which is equivalent to 20 gigahertz or double spacing. The effect of the Brillouin wavelength on the number of channel optical signal to noise ratio and stock peak power is investigated when we increase the wavelength from shorter wavelength to the longer wavelength is investigated, and the Raman power is set at 1100 milliwatt, and the Brillouin wavelength power is set at 11.8 dBm. As shown here in this figure, the Stokes line count decrease gradually with the increase the wavelength from shorter to the longer wavelength because of the spectral broadening at the shorter wavelength and the saturation of the signal at the longer wavelength. As we increase the power, as we increase the wavelength from as we see here at 1631, there is about 298 channel is generated and decrease gradually to reach 244 channel at 1640 nanometer. So also when we increase the Brillouin wavelength from shorter to longer wavelength, the average optical signal to noise ratio increase gradually, because when we increase the wavelength from shorter to longer wavelength, the number of channel is decreased. So the average optical signal to noise ratio increase because of the energy become enough to separate the self-losing mode and increase the average optical signal to noise ratio. So as we see here, when we set that the wavelength at 1631, there is about 20.41 dB average optical signal to noise ratio, and increase gradually to reach 22.22 dB at 1640 nanometer. So an optimization is the second objective of our work. So we try to find the best optical signal to noise ratio with high number of channels. So at this wavelength 1640 nanometer, about 244 channel is generated with 22.22 dB average optical signal to noise ratio. Here is the optimum wavelength, which generates this Stokes line with this average optical signal to noise ratio. Also, the stock peak power is investigated when they increase the Brillouin wavelength from shorter to longer wavelength. As we see here, as we increase the wavelength, the Stokes peak power is increased gradually because the number of channels become less and energy become enough to separate self-losing mode and increase the stock peak power. Moreover, the Brillouin tunability is investigated when the Raman power is set at 1.1 watt and the Brillouin power is set at 11.8 dBm, and the Brillouin wavelength is changed from 1631 to 1640 nanometer. So at this tunability, the Brillouin wavelength can be tuned over 9 nanometer as shown here. So we cannot tune over 1640 nanometer because the variable bump, Brillouin pump in the lab cannot be tuned over 1640 nanometer. If we have bump with more tunability, the tuning rate will be increased. Here is the Brillouin tunability magnified view, which shows the same as the previous spectrum, but in the large view from 1631 to 1640 nanometer. Also, the optimum signal to noise the optimum signal spectrum is investigated when the Raman power is set at 1100 milliwatt, and the Brillouin signal is set at 11.8 dBm, and the Brillouin wavelength is set at 1640 nanometer. So at this parameter, the total number of channels generated is about 244 channels. Of this total channel, there is about 240 flat channels generated over 41 nanometer bandwidth. So for this spectrum, a large view of the spectrum at the beginning of the spectral comb is shown in this figure B, with the average optical signal to noise ratio of about 22.2 dB, and at the end of the spectrum shows here is the magnified view with an average optical signal to noise ratio of about 22.2 dB, with a discrepancy between even and odd signal of about 22 dB. The signal stability and Raman power to Stokes conversion efficiency is investigated. So here the signal stability is an important precondition for the DWM application. So we test the signal stability at 3 wavelength, while the Raman power is set at 1100 milliwatt, and the Brillouin wavelength is the Brillouin power is set 8.8 dBm, and the wavelength is taken at 3 wavelength, which is lambda 1 1650 nanometer, which has 0.5 dB fluctuation, and the second wavelength in the red color at 1660 nanometer, 0.4 dB fluctuation, and a third wavelength which is lambda 3 1675 nanometer, which we have 0.6 dB. This is taken, the measurement taken by the author because of the background error that does not allow us to implement the optical power meter at 1550 nanometer. Then the total output power stability is investigated over 1 hour using the optical power meter. The measurement is taken by using optical power meter, and here is the result, shows about 0.12 dB as a fluctuation from a maximum of minus 15.42 to maxima to a minimum of minus 15.552. As we can infer from this signal stability that the result shows a good stability and can be used for optical communication and optical sensing. Finally, the Raman power to the output power is investigated. As shown here, as the Raman power increased, the output power also increased linearly to reach at 1300 milliwatt to reach about 45 milliwatt at the output power. So here is the experimental in the blue color and the fitting line in the red color. Here is the 700 power threshold, and the Raman power to Stokes conversion efficiencies achieved is about 5%. The performance, finally, the performance comparison and summary. Here is the performance achieved for the previous work, and we compare it with our work. Here is the performance summarized for the previous work, which is only one paper that is in the U-band using Brillouin-Raman fiber laser, which reported about 136 flat channel with 23 nanometer flat bandwidth using 2.26 watt as a Raman power, and this is reported on reference number 5. So in our work, we have reported 240 flat channel using over 41 nanometer bandwidth using 1.1 watt. As we see here from this result, our work outperformed the previous one that is achieved in the U-band. So to date, this is considered the best performance that has been reported on the U-band region. To summarize, the proposed design shows an excellent performance in terms of number of channel, signal to noise ratio, output signal stability, and laser efficiency. Therefore, this system is suitable for practical applications such as optical communication and optical sensing. Here is a references for the problem statement and the literature review, and there is more references on the report. And this is a certificate which shows the proof of publication of our work 2 months ago. Thank you for listening, and I'm ready to answer any question.